promises to be insightful, addressing how system control drives stability and sustainability in energy management. Let's embark on this journey together to understand the pivotal role of system control in ensuring energy security for Sri Lanka. It is an honor to introduce our esteemed guest speaker for today, Engineer Dhanushka Bandara, Operation Engineer at the Upper Kotmale Hydropower Plant, CEB. Engineer Dhanushka brings a wealth of knowledge and experience, offering invaluable insights into the operation and control of our national grid. He will guide us through the complexities, challenges, and innovations in this domain, highlighting the importance of coordinated system operation in empowering Sri Lanka. Please join me in giving a warm welcome to Engineer Dhanushka Bandara. Sir, the virtual floor is yours.
Thank you. Good evening to all. So let me share the presentation. So sorry for the disturbances. We'll just start. So this presentation actually not made by me. It's made by the power system engineer Kasun Pereira. This is the one. Sometimes you might have come across with this. So I am Dhanushka, operation engineer from Upper Kotmale. I will just present for you because this is the latest presentation with the updated data, right? So we are going to look at the National System Control Center, and some of you can keep your mics on. So do not mute because I would like to have an interaction with you. Okay. Otherwise, because there's some technical disturbances here, sometimes I might lose the connection. So it's better some of you, if you do not have any background noise, you can keep your mics unmute, right? So this is just the organization structure of the System Control Center. So you don't need to know much about this. Just you can understand there you have the planning division and the operation division and the audit division, right? So meaning of the planning division is now you know the System Control Center in any organization, you have the planning section, right? So after once you have planned, then only you can have the make it real. So that means in order to have the operation, first of all you have to have the plan, right? So operations division is the one which take the responsibility of real-time operation, right? So once the operation happens, so then they collect so many data, set of data. So then there's an audit division in order to analyze those data. So this audit does not mean something like the audit you are referring in accounting, right? So this just describe you the function of each sections, right? Operation planning and system operation and operation audit, right? So we'll move fast because I just want to focus on some main topics. This is just the AC power system, right? You might have the idea about the AC power system. It consists basically three divisions: generation, transmission, and distribution, right? So basically, why you have this three type of section is that you can say because of the voltage. Usually the generation voltage in Sri Lanka, it is somewhere in between somewhere 6 kilovolt to 20 kilowatt, right? Then the transmission network, if you consider in Sri Lanka, it is 220 kilowatt or 132 kV voltage, right? So then the distribution is 33 kilowatt or 11 kV, right? So what is happening is that, so you are generating some voltage below the 20 kilowatt, So then before transmitting, you have to step up. So can someone tell me what is the reason for step up? Why we are going to step up the voltage? Hello? Can someone tell me what is the reason for stepping up?
Uh, Excuse me, sir.
Yeah, just tell me.
Yeah. To the reduce power loss.
Yeah, one reason is that reduce the power loss, right? So by increasing the voltage, what you are trying to do is that decrease the current. So by decreasing the current, it will reduce the power loss, right? So that's the one reason, right? So we step up. Then the issue is that once you step up, the consumers can't use it, right? 220 is a high, 220 and 130 is a high voltage. So consumers can't use it. So what we have to do is that again we have to step down, you know. So step down take place in the place we are calling it as, actually here it is substation. In Sri Lanka, we are calling it as a grid substation, you know, grid substation. So that is the place where that 220 or 132 kV kilowatt voltage step down into 33 kV or 11 kV voltages. You know, 33 kV or 11 kV voltages. Even 33 and 11 kV voltages, there are few customers directly use those voltage because they have their own transformers. Otherwise, if you consider the domestic customers, so they can't use it, right? 33 and 11 kV they can't use. Therefore, you might have seen another set of transformers you might have seen side by the road, so on top of poles, right? The small transformers. So those transformers are the thing which can step down again from 33 to 400 voltage. 400 voltage. Then finally, the 400 voltage means it's a, you know, the three-phase voltage. So if you have the single phase supply, you are getting 230 voltage. You know. So that is what happened in the power system. So then, so in this power system, the system, why you have the system control is that, you know, that from the generator or in the power station, you have something called a synchronizing breaker. That is the circuit breaker which connecting into the transmission network. So from that synchronizing circuit breaker and up to this 33 kV circuit breakers at the grid substation, you know. So from the synchronizing circuit breaker from in the power station to the 33 kV feeder circuit breakers at the grid substation is controlled by the control center. You know, it's controlled by the system control center. So in all countries, not only in Sri Lanka, you might find out that in any power system, any AC power system, there should be some control center which has the authority to control the circuit breaker and generation. Right? So you will see why in coming slide, right? So this is just the overview in our power generation system. Actually, we have somewhere 27 power station, right? 27 power station. You can see it's a very small number. So out of that 27, the hydro power station are 16, and thermal power station again you can divide it into CB owns one and the IPP owns. Do you know what is IPP? What is mean by IPP? Can someone tell me what is mean by IPP thermal?
Independent
CB thermal
power
mean?
producers.
Sorry?
Independent power producers.
Yeah, independent power producers. Those are the private owned power plants, thermal power plants, right? So at this moment, I think there is only two power plants. You know, there's only two power plants owned by the private sector. But two power plants means two thermal power plants owned by the private sector, right? And you can see that if you compare with the number of power stations, we have many grid substations. There's about 80 plus, 18 plus, 80 plus grid substation. You know, so this is just the overview of the generation system. Again, that's the install capacity, right? No? Install capacity, you might have the idea about what is mean by install capacity. That means when they are commissioning a power plant, right? No? So they have the design capacity. So that is the install capacity, you know. But what is happening is that sometimes actually when it comes to operation, you can't utilize that install capacity, right? So in terms of install capacity, the conventional hydro means the major hydropower plants, and mini hydro, CCP mini hydro means that is a very small mini hydro. We are defining as a hydro plant if it is less than 10 megawatt. So see, there are 3 power plants which are owned by CB. So that total is here 20 megawatt, right? Then CB thermal means, there are a set of thermal power plants operated by the Ceylon Electricity Board. Then this is IPP thermal, and finally you have something called NCRE. So can you see the NCRE is 1825. So compared to the conventional hydro, the NCRE amount is more than. So what is mean by the NCRE? What is it stand for NCRE?
Non-conventional renewable energy.
Yeah, non-conventional renewable energy, right? So you can see that it is more than our conventional hydro installed capacity, right? So this in non-conventional renewable energy include mini hydros and solar. Solar basically rooftop solar. Plus there are some private owned solar plants. Plus wind power plants. Wind power plants. And important thing about this NCR is that those are operating independently. And that control center that we are talking about do not have any control over these power plants. For example, if you consider just a mini hydro, it operates as they wish. If they have the water, they can operate. So there is nobody to control it, right? So that is the difference between this NCRE and rest of the power plants. So in other way, the control center has the control only about this top 4. They don't have any control about this NCRE, right? Then, so this figure is somewhat important because this is the total installed capacity in the country, right? It's some more than 5,000 megawatt. Then I'll skip these slides because this just describes the hydropower stations. And if you consider the hydro generation in Sri Lanka, basically we have 3 systems, 3 complexes. That means Lakshapana, Mahaviri, and Samanala. So Lakshapana complex means there are a set of power plants, hydropower plants built around the Kalani Ganga. So Kalani Ganga, you might have known it already. So Kalani Ganga formed by the two which is called the Kehelgamu, and the other one is Muskelioya, right? Muskelioya. So by crossing Kehelgamu and Muskelioya, they have built 2 reservoirs, Kasari and Mausakale, right? So after that, so there the Vimalaswanda power station which takes the water from the Kasari reservoir, Then when you know that when you have the hydropower station, there should be some reservoir to take the water, and again there should be some place to discharge the water. So in this case, the Vimalaswanda power station discharge the water into the Norton Pond, From the other side, Canyon power station takes the water from the Mausakale and it discharge the water into the Canyon Pond, right? So like that it continues. You can just have an idea. So here the important thing I want to emphasize is that Kasari and Mausakale is called as the reservoirs, and all other these reservoirs actually called as a ponds. The Norton Pond, Canyon Pond, you can see Lakshapana Pond and Bodland. So why we are calling those as the ponds? Do you have any idea? What is the reason for naming those as ponds and only the Kasari and Mausakale as reservoir? So it is actually because of this capacity, right? You can see the capacity. This Kasari reservoir capacity is 48 MCM. So MCM means what? What is mean by MCM?
Million cubic meter.
Million cubic meters, right? So this capacity is the million cubic meters. So that is in terms of capacity of the water, right? Capacity of water, then you can compare the capacity of the pond. I know it is very small amount, right? 0.4. So that is why we are calling it as a pond. It's because of its small capacity, right? Then you can see some this yellow color labels. So this is much important value, right? So when in a hydropower station, so this discharge rate is a much important parameter, you know. So this is the discharge rate of the Vimalasurendra power station. So you can see the unit of it. That says what? Cubic meters per second per megawatt. That means if you are operating this Vimalasurendra power station at 1 megawatt, so per second, during a 1 second time, this much of water, 0.566, will be discharged. You know, so this value is much important because if you consider, for example, this Norton pond, you know, it gets the water from the water due to the operation of the Vimalasurendra power station, and it lost the water due to the operation of the Old Lakshmana power station. You can see if you consider this Norton pond, the two power stations are connected. You know, two power stations are connected. One power station discharge water into the Norton pond, then Old Lakshmana takes the water from the Norton pond. You know, so therefore this discharge rate is important in order to balance the pond level. So balancing the pond level means you have to avoid the spilling and you have to avoid the water level drop down to MOL. MOL means minimum operating level. So each reservoir, so once it is connected to your power station, we can define some level which has the MOL. MOL means minimum operating level. That is the minimum level that required in order to operate the downstream power station. You know, so you can't drop down the water in the reservoir beyond that MOL, minimum operating level. You know, so therefore this figure, discharge rates are important in the case of balancing the pond levels. You know, another important thing is that you can convert this amount of water into energy. You know, into energy. So usually we are talking, because the water is the one we are using for the electricity generation. You know, in the case of hydro generation, usually we are not referring these reservoir capacities in terms of MCM. So we are talking it in terms of gigawatt hours, or usually gigawatt hours. So can you convert this 48 MGM into gigawatt hours? You know how to do it. What we have to do if you want to convert this 48 MCM into gigawatt hours? Can someone just convert for me? How we can convert this 48 MGM into gigawatt hours? Any idea? So this Kasar reservoir is connected to the Vimalasurendra power station. You know, so there's only one power station. It generates the power. So its maximum capacity is 50 megawatt. I know its discharge rate is given. So how you can convert this Kasar reservoir capacity into gigawatt hours? Any idea? I again repeat, this discharge rate means
By dividing discharge rate capacity.
by dividing
Discharge rate capacity.
you have to divide this 48 by the 0.566, right? Understand? Yeah, you're correct, right? So 48 MCM should be divided by this 0.566. Then what will happen? It will convert it into megawatt seconds, right? Megawatt seconds. Again, you have to divide it by 3600 in order to convert into hours. So then it will convert into megawatt hours. Right now? Megawatt hours. So like that. So actually, so you'll get some value in terms of megawatt hours, but it is actually not correct. Why is that? Is that all we can generate from this water? So if you divide this 48 mcm by this value, it will give you the total megawatt hours that you can generate from the Vimala and the power station. Is that all? So what happened once that water go through the Vimala and the power station, it will come into Norton Pond, then it will go through the Old Lakshapana power station also. Right? So after that it will come into the Lakshapana Pond, then again it will go through the Old PTA power station also. Then finally it will go through the Broadland power station also. So water in the Kasari reservoir can be used to generate not only at the Vimala and the power station. That water will be used at the Old Lakshapana power station, at the Polpitia power station, and at the Broadland power station. So, like you have converted this water into megawatt hours using the discharge rate at the discharge rate of the Vimala power station. Same thing you can do with the discharge rate of the Old Lakshapana and Polpitia and Broadland. Then only you will get the real value of the energy value, real energy value of this Kasari reservoir. Right? So that you have to keep in mind. So in a cascade system, so how you are going to convert the water the capacity or the water capacity in the reservoir into gigawatt hours or the energy. You have to consider the all the power station in the downstream, because the same water will flow through all the power station. Right? Have you got it? Hello?
Yes.
Yeah, have you got it? Okay. So this is just the Mahali complex. Mahali complex means the hydro stations that have been built along the Mahali Ganga. So it's the begin with the Upper Kotmale power station. You know the Kotmala is the one substream of the Mahali Ganga. Then by blocking the Kotmala area, they have made some small. It is again a kind of pond, right? 0.8 mcm. Then which is located in Talawakale. Then by taking the water from this reservoir, Upper Kotmale reservoir, the Upper Kotmale power station is operating. It discharges the water into the Kotmale reservoir. Kotmale reservoir is somewhat big one. Then you have the Kotmale power station. Then Kotmale power station discharge the water into the Mahali Ganga, right? Mahali Ganga. So then, if you know the route of the Mahali Ganga, so it will come to Polgol. Okay, it will flow through the Kandy. Then at the Kandy, there's a diversion dam. So what they have done is that they block the Mahali Ganga, and you will get another kind of pond, which is called a Polgol pond. From there, they have built a tunnel to the Ukwela. Then Ukwela power station is operated by using the water in the Polgol pond. So that is why we are calling that that Mahali project, right? Mahali project. The main purpose of the Mahali project is to divert the water in the Mahali river into the northern sector of the country. So this is the point where they have diverted. So after the Polgol pond, you have the Victoria reservoir, then you have the Victoria power station, and the Rantingal power station, and finally you have the Rantaway power station. So after the Rantaway power station, there is something called Minipe, right? Minipe Anical. So they are onward, they release the water into the Mahali zones, right? So in the other side, after the Ukwela power station, you have the Botan reservoir, then you have the Botan power station, then you have the Moragahakanda reservoir. So there actually you have a small, I think 25 megawatt hydro generation. Those are operated by Mahali Authority. Then again, water will be released into the another set of Mahali zones. So this is the Mahali complex. So you have to understand that the Mahali complex actually the main purpose of the Mahali power station Mahali project is just to store the water for the irrigation purposes. So this power station are actually byproduct of that Mahali project, right? So therefore, this only the power station are belongs to the Ceylon Electricity Board. These all reservoirs are belongs to except this Upper Kotmale reservoir. All other reservoirs are belongs to Mahali Authority. So they are operated by the Mahali Authority. So then quickly move to the Samala complex. So Samala complex means the rest of the power plant actually. So if you can forget about the Lakshmana complex and the Mahali complex, all other power plants are belongs to Samala complex. This Samala means just the name given because of the Samala power station. So using the Valayaganga, there is a two power station, Samanala power station and the Udawale. And other than that, you know the Kukuleganga, that's again another runoff river type power plant. Kukuleganga means it's a substream of Kaluganga, right? Kaluganga. So there you have the Kukuleganga power station. And other thing, Umaya, actually Umaya was here also, I think it's wrong, right? Umaya officially belongs to Samanala complex, right? So these three power plants belongs to the Samanala complex. Then these are just the irrigation release, because I told you that Mahali project main purpose was that releasing water for irrigation purposes. So these are the main points where you have the irrigation releases, right? Irrigation releases. And when it comes to thermal power generation, so you might have already known that the biggest power plant in the country is the Lakpija coal power plant. Its capacity is 900 megawatt. Then you have the Kalanthissa power station. There you have the many, actually not only one power station. There are many, I think 2 combined cycle power plant and some gas turbines are there. Then Sabugaskanda power station is just the kind of diesel generators. Then Baj Mountain power plant also kind of diesel generators. Uttujani also kind of diesel generators. Then you have the CB emergency means again other kind of diesel generators, right? Then in the private, when it comes to the thermal power generation in the private plant, you have now West Coast power plant. This one is old one. Again, it's a kind of gas turbine. There's 2 gas turbine and 1 is steam turbine. It's a combined cycle power plant. And Sobadane one is the latest one. Actually, it was intended to operate from the, you know, that liquid natural gas LNG, but still they haven't built that LNG terminal. They are now, this one is operating using, I think, diesel, right? Using the diesel. And this is again just the about the NCRE, non-conventional renewable energy, right? So we'll move into quickly. This is just the daily net electrical generation in a particular day. Actually, you can see all this data in our website. You know, that's cb.lk. So daily they are uploading the previous day generation statistic, right? So this is just the data on the December 4th, right? So on that day you can see that so more than, I think, 50% of the daily generation has been accomplished using the hydro generation. So here you can see the total net energy. So if you consider that particular day, the daily generation is 47 gigawatt hours. 47 gigawatt hours. Then this shows you the what is the generation mix. CB hydro is 27, and here somewhere you have the mini hydro. SPP mini hydro is 5, right? That means somewhere about 32 gigawatt hours are from hydro generation. You know that because now you have to understand that this is not always the case. This is just because that December 4th is a wet day where they have got the much water inflows in the reservoirs, right? And this just show you the demand behavior during 1 year, right? During 1 year. So average is 42 two, and the two graphs is there just to show you the net generation and gross generation. So what is meant by this net generation and gross generation is that you know that all power plant, power station will have their own auxiliary consumption. So gross generation means with the auxiliary consumption, net generation means what is available to the customers, right? So there's a small difference there. Anyhow, what you have to understand is that the daily average. So if you consider this is just the 2023, so daily average is somewhere about 43, okay? 43 gigawatt hours of energy, gigawatt hours is required in the country. So it is a demand. So per day, 43 gigawatt hours, right? So that means this much of energy has to be generated. Again, this will show you the monthly net generation. Again, it is on the 2023, you know. So you can see that it's monthly, right? Monthly and the generation mix. So you can see that if you consider January, February, March, you know, the somewhere up to September, the hydro generation is smaller, and you have the more thermal generation, you know, more thermal generation, and you can see that in October, November, December, the hydro generation has been increased. So that because they have got the much inflows or much rainfalls. And this one again, just the energy mix breakdown. We'll quickly move. And this one is important. This is just the system operation policy, you know. So in Sri Lanka, the frequency of the country is 50 hertz, you know already, you know. So it is allowed to move in between 49.5 and 50.5. That means there is a 1% tolerance, you know. So the system frequency can be in between 49.5 and 50.5. Then when it comes to the voltages, so this defined for the transmission voltage and the distribution voltage. I told you earlier, the transmission voltage is 132 or either 220. So there you can have the 5% tolerance, and for the distribution voltage, it is just the 6%, right? So yeah, 6%. So they have defined for the two cases, the single contingency and the normal system condition. I don't think you have an idea about the contingency means. I'll just skip it because it will take time to explain, right? So again, this one is the much important thing, right? So this is the policy they used for the operation of the power system, you know, operation of the power system. So the first priority is for the safety of person, then the protection of equipment, then the availability of supply, then quality of supply, then economy of supply. So you'll understand. So you'll understand that safety of person, the first one is the safety of person, then protection of equipment, then only you'll have the availability of supply. This means that, for example, if these two conditions are satisfied, only we can have the availability of supply, you know. Now, for example, let's say you know that already that when you have the flooding, I know we have to switch off the feeders, I know, for the safety of persons, you know, or we have to give the first priority for the safety of person. Now, in other case, for example, let's say there's some fault in the power plant. Let's just consider the coal power plant, right? Norway. So if they have identified some fault, you know, so if it is damaging the power plant, what they have to do is that they have to stop the power plant, right? They have to stop the power plant. So because they have to give the priority for the protection of the equipment or protection of the power plant, you know, then only we can have the availability of supply. If the safety of person and protection of equipment is satisfied, then only we can have the availability of supply. If the supply is available, then only we can have the quality. So without having the supply, you can't measure the quality. So in this case, quality means, so they have to supply the 50 hertz voltage within the agreed voltage, agreed tolerance of the voltage. Usually in Sri Lanka it is called as 230 voltage, right? There's a particular tolerance. So within that limit, electricity board has to supply the voltage. Then finally we are talking about they're considering about the economy. The last thing they are considering is the economy. That means at whatever cost, what you have to understand is that because the availability of supply is at the third place, so at whatever economy at the last place, at whatever cost, they are going to supply you the electricity. So that is what you have to understand. So if this economical supply comes somewhere in the third place or in the second place, what will happen is that before supplying, they will consider the economy. They can consider the economy means they will consider the cost of the supply. Cost of the supply. Now, in our case, what has happened in this country? So they consider the cost at last. So that means the government policy is that they will try to supply electricity at whatever the cost, at any cost, right? And this is just the demand curve. This is how the electricity demand in the country changing. You might already know it. So I'll just quickly go through it. So if you consider a particular day, the minimum demand is recorded during the off peak. Off peak means during the night time. During the night time, somewhere in between 2 and 3 a.m., you'll have the minimum demand. So that is we call as the off peak. Then after that, what will happen? Somewhere around 4 o'clock or 4:30, what will happen? People are getting up, so they switch on the lights. They are cooking, right? So then gradually this electricity demand is keep on increasing, and finally somewhere between 5:30 and 6:30, you will have the something called the morning peak, right? That is the after somewhere around this morning peak, what happened is that demand is keep on decreasing because it's that sunrise, then you are switching off the light and you are leaving the homes. And now during this period, actually you are on roads, right? Most of the people are on road. So the students are going to schools, right? So therefore what will happen? This electricity demand will decrease. Then again, what will happen after somewhere 7 or 8 o'clock? It keep on increasing because now they have reached their factories or their offices, right? Then again they start the works. So the electricity demand keep on increasing. And finally somewhere in between 11:30 or 12:30, you will have the day peak. And here you can see a small drop there after the day peak. That because actually, that most of the factories are stopping the work for the lunch, right? Because of that, you can see this small drop there. After again 1 p.m. or 1:30, it start to increase. Then again you'll get another peak here, and finally after 4 o'clock there's a small drop. Then again what is happening? So after 5:30 or 6, it keeps on increasing at rapid rate. That means, so that people are going home again and they're switching on the lights and switching on TV, right? So then you'll get the maximum demand demand on the day, somewhere around 7 p.m. So that is we call as the night peak. So that is the maximum demand on particular day. So after that, what happened? It is not actually prevailing for a long period. It's for a very small period. Then what will happen is that it start to drop. You can see a huge drop there. So if you consider this night peak as 2,500 megawatt, you can see it keep on dropping, and finally reach somewhere 1,400. This is just for a particular day, right? So, but you can see somewhere about 1,000 megawatt drop is there. So in Sri Lanka, this demand curve is actually totally depend upon day-to-day activity of a people, because we are, that we are not a developed country. So if you consider another demand in another developed country, that won't be like this. It will be almost plateau. You know, it will be almost plateau. Now, in our country, you have the huge variations, because in our case, our electricity demand is totally or mostly depend upon the day-to-day activity, or most of the consumers are the domestic consumers. That is the reason we don't have the much industrial loads, right? Then, so this again an important thing. We have something called the base load. You might have already heard that base load plants, right? So base load means the load or the demand which prevail throughout the day, which exists throughout the day. So that is called as the base load. So then you have the intermediate loads, and finally you have the peak loads, peak loads. So sometimes you might have heard that there are when you are talking about the power plants, they are saying the base load plants and peaking plants, right? So peaking plants are the one which has the highest cost if you consider thermal plants, So base load plants are the much cheaper one, and the peaking plants are the much highest cost plants. And this is just the weekly demand curves of 2020 from 2020 to 2023. I think they must have drawn it using the same 7 days, right? Same 7 days. But what you have to understand is that what has happened to the country. So this red color one is a 2023. Yeah, light green one is the 2022, then 2021 and 2020. So what you can understand is there's a huge drop in the demand, right? From the red color one, either if you compare these night peaks, you can understand there's a huge drop in the demand, So that actually because of what? The economical contraction in the country, With that economic crisis, what has happened is that demand for electricity has been decreased. So then this will again explain the same thing, right? Same thing. So I will leave this on. This just compare the wet and dry day, So in a wet day, you have the more hydro generation. In the dry day, you have the more thermal generation. That's all. So these are just some figures you can find out. And this is much important thing that we have to discuss: supply and demand behavior in a power system, right? So already, I think you know this power triangle. What actually what we are going to talk about is active power and reactive power, right? The supply and demand means about the energy, or in terms of electrical power. Power means actually there's a demand for the active power and demand for the reactive power also. So we are just talking about the demand of reactive power and the active power. So can you tell me what is mean by reactive power? You might already know that what is active power. Is there any demand for reactive power? What is mean by reactive power? Can someone explain what is mean by reactive power demand? Active power demand means what is the power required by that heaters, irons, there's a real power required. What is mean by the reactive power? Is there any demand for reactive power, or is it only for the active power?
It is only used for transmission voltage compensation.
It is used for
Transmission line voltage compensation.
reactive power.
Yes.
Yeah, that's one use of reactive power. Just I want to know is that whether there's a demand for reactive power. Is there any consumers who are now, for example,
It's
if you consider
consumed by inductive loads.
inductive loads, right?
Yeah.
So reactive power is consumed by the inductive loads. So that means anywhere you have the motors, right? Pumps or whatever kind of inductive loads, they need the reactive power. They need the reactive power. Therefore, in the country, if you consider consumers, there's a requirement for reactive powers, as well as the active power, right? So in a power system, both reactive power and active power should be supplied or should be generated, right? That's what you have to understand. Now, what we are mainly talk about is the active power balance. How we are going to balance the active power, And this again, you might have already know that because this is, you should have any idea in order to understand what is happening in the power system. So this just explain you the power flow. This is just the power flow equation, when you have the two voltage sources. So this is sending in and receiving in, whatever the two voltage. Actually, no need to be source, right? Wherever you have the two voltages, you can consider this as a two bus bar. Wherever you have the two different voltage, there will be a power flow in between. There will be a power flow. So active power flow is given by this equation, and the reactive power flow will be given by this equation. The important thing is that the active power flow will depend upon the ES, ER, and XI. These are voltage magnitudes, and X is the impedance. And the much important thing is that this delta. Right? So these are magnitude means just the positive values, right? So delta is the angle difference of the two voltage. So in this case, as they have defined the one voltage as 0, you are just getting the delta here. If you have the delta 1 and delta 2, what should be here is the delta 1 minus delta 2. You have to understand that this delta means the angle difference, right? So therefore, depend upon the angle difference, it will decide the direction of the power. So how the power is going to flow, whether it is from this left side to right side or right side to left side. The direction will be defined by this delta. Or in another way, the active power is flowing from higher angle to the lower angle. That's what you have to keep in mind, right? Wherever you have the higher angle, active power flow from that point to the lower angle point. If this is 30 degree and if this is 15 degree, so what will happen is that active power will be flowing in this direction. And when it comes to the reactive power is flowing where you have the higher magnitude of the voltage to the lower magnitude. So it will consider only about this voltage magnitude. So let's say at this bus bar, let's say the 220 volt is now 230, and here if it is a 220, what will happen is that the reactive power will flow from this 230 bus bar to 220 bus bar, from higher voltage magnitude to the lower voltage magnitude. So therefore, what it is possible to flow active power in one direction and the reactive power in the other direction, right? That is possible. So this is just you might have already know this one. This is the transmission network, the latest one. So this I just shared it here because to get an idea. So what you can basically see here is that you can see the two color lines, right? One is the purple color, and another one is the green color. The purple color lines are the 220 kilowatt lines, and the green color lines are the 132 lines, right? And you can see the small squares here. The small squares represent, I think those are the grid substations, and there you can see the circles. Those circles are represent the power station, power station. Then from this figure, which part in the country do you think will have the highest power, highest demand? By looking at this map, you can understand the country from where you are getting the highest demand for the electricity.
Colombo.
Colombo, right? The western province is the where you have the highest demand. So we consider actually the western province as the load center. That's why you can see there's so many grid substations there, right? So if you consider this northern part, actually it is somewhat about 1/3 of the country, only you have 1, 2, 3, 4, 5 grid substation to supply here. Can you see? Because the demand is less there. demand is less. And another thing you have to figure out here is that if you consider Mahali complex, the Mahali hydro generation, it is located somewhere here at the center. You can see that Kotmale, I don't know whether it is clearly seen by you, the Kotmale, Upper Kotmale, Victoria, Randanikala located in the middle, the middle. And again, if you consider Lakshapana complex, it's somewhere here, hydro project, So what should happen is that whatever the generation should flow to the Colombo. So because Colombo is the load center, so the western point is the load center, basically more power from this hydro generation will flow into the Colombo. So this Kotmale Biagama line is one critical transmission line in the network, it takes the power from the Mahali generation to the western points, western points. So this is again the same transmission network in another form, right? This is what they are using the control center. So the line length are not actually representing the actual length, right? Actual length, but if you consider the positions, right? This left side is shown the southern part, and the right side is shown the northern part, and top part is shown the grid substation located in the western points on the western side, and the bottom one is the eastern side. It resembles somewhat the same map, but not exactly. So what you can see here again is you can see the green color lines and the blue color lines, right? So blue color ones are the 132 voltage, and the green color ones are the 220 lines. So you know that when you have the 2 voltage in the transmission network, there should be some mechanism to connect them, because the 2 transmission levels. So how they are going to connect those 2 network? Because 220 network and 132 network should be connected. Can someone tell me how they are going to connect it?
By using interbus transformers.
Interbus transformers, right? So by using the interbus transformers, they can connect the 220 and 132 network. So that interbus transformers are much important, because those are the places where act as a dose, or whatever the generation you are pumping into the 220 network should be come down, so should be flow down to the 132 network, because there is nobody consuming the power in the active power in the 220 network. No consumers are connected to the 220 network. All are connected to the 132 network, or in terms of 33 kilowatt. So therefore, whatever the generation you are pumping into the 220 network should come down to the 132 network. Then from the 132 network, it should go to the 33 kV network or the distribution network, then only to the consumers. So therefore, these interbus transformers are much important. Can you figure out the places here? Is it clear, this diagram to you? Can you figure out? So there are a few places you can figure out where you can identify. These boxes are the grid substation or power station. There you can find out some boxes where you are getting the green color and blue color lights. Places you have the both blue color and green color lines are the interbus transformers. Can you figure out at least one or two?
Biega.
Yeah, BA gamma is right. So somewhere here BA gamma you can see. So it's a one place where you have the 220 and 132 connection. Again, somewhere here Kotuvada, you have the 220 and 132 connection. Then when it comes to the New Chilau, you have another place. So 1, 2, 3, Then at New Anuradhapura, there is another one. Okay? Then at Rantaway, there is another one. So 1, 2, 3, 4, 5. And somewhere here Pandipiti, you have another. 6, and Kalant is also another one. So only I think 7 or 8 places there, which connects 132 and 220. And somewhere here a new connected one, new pulpit also. There you have the 220 and 132. Here Hambantur also you have the 220 and 132. Correct? Those are the interbus transformers. And another thing is that, so you can see that always in almost places you have the 2 lines, right? all the boxes, all the grid substation are connected with two lines. Why is that? What is the reason for these two lines? For example, if you consider Kotmale Biegama, there's a two transmission line, right? Kotmale New Harbour, there is again two transmission lines. What is the
Double
reason?
circuit line.
Sorry?
Double circuit line.
Yeah, double circuit. I mean, what is the reason for that? Why you have the two transmission lines instead of having one transmission line?
The other is used as backup.
Yeah. So usually why you have the two transmission line is that if one line trips, right, or if one line break down, if there's any breakdown or if there is any tripping, the other line should be able to take that power. Otherwise, what will happen? If you have only one line, for example, if that just consider Kotmale Bigama, suppose you have only one line, then if that line is tripped, what happens? There is no way to transmit this power from the Mahali complex to the Biegam, you know. So it has to find out then another path, you know. Actually, these two lines are there because of the system reliability. In order to keep the reliability, we call it as n-1 reliability. N-1 you already know, right? If one component fails, the rest of the things should be able to carry out the system. You know, so that's called the n-1 reliability. You know, so that is why almost everywhere you have the two transmission lines. You know, and further, if you're going to analyze this network, you can see that this Mahali generation are located somewhere here. This Kotmale, Upper Kotmale, Victoria, Ranjanigal, Rantagola, stepping up to 220. Right now, then this whatever the generation that's pumping into the 220 network should flow somewhere. You have the consumers, you know, consumers. So can you identify the path? Actually, there are I think 3 or 4 paths, right? Where this Mahali generation can flow. The one path is Kotmale to Biegam, you know. Whatever the generation from the Mahali complex or hydro generation here can flow to the BA gamma, then it can come to the 132 network, and it can go to the Sapuaska, the Calania, like that. Those are grid substations. Then from there, 3 kV, you know, like that, that power can flow. What is the other path? There's another path. What is it? Are you following me? So what is the other path?
New Habarna Anuradhapura something.
New Haryana, Anuradhapura, yeah. Right, very good. So other path is the New Haryana, Anuradhapura. Whatever the generation can flow to the New Haryana, then New Anuradhapura, then from New Anuradhapura it can go to the 132 network, I know. Then there are so many substations you can see about New Anuradhapura, Upper Kinochi, Trinco, like that. So those are the one with substation. There you have the 32 kV feeders, I know. Then they can find the consumers, you know. That generation can find the consumers. So that is the one part, you know. There's another one. What is that? There's another one. Can someone tell me?
Through Victoria Power
Sir?
through Victoria Power Station.
To Victoria to
Ranjanigal Rantam.
Rantan, right? So Rantan is another one. So basically, Mahali complex, Mahali generation has 3 parts, right? One way to Biagama, other way to Nimonadpur, other way to these Rantan coupling transformers. It can go to the 132 kV network. You know, that is important because in the latter part we are going to discuss about the total failure in 2023. So you have to keep in mind because it is important to understand what has happened there. I know. Basically, there's only 3 parts for the Mahali complex generation. You know, so like that, if you consider this Lakkija power plant, you can see the Lakkija, that is the highest or the biggest power plant in the country. 900 megawatt is there. So there's only 2 parts, right? Can you see? So from Lakkija to New Chilao, then we am going to Kotugal, like can come, you know, or other way. it can go to the Numanadapur, then New Habagana, then Kotmale, then Biagam again. That's another path, you know. Got it? So this transmission, Bayangod and New Habagana lines are, I think they have not yet constructed, right? So at this moment, there's a two path, you know. So like that. So that number of paths for the power flow is important, right? Now, so if there's any failure in one path, other path will be loaded. I know other path will be loaded. And if you consider Lakshapana generation, so here you have the Lakshapana, or Lakshapana, now Lakshapana, here. Those are the Lakshapana generation. So now Lakshapana generation basically comes to the Colombo via these 132 kV lines to the column now. So that is the way for the find out the load centers. I know. So basically these four transmission lines, right? Four transmission lines to Atugiri and Kostam and Sita, you know. So these four transmission lines are again critical because those four are the one which takes the Lakshapana complex generation into the Kolonava. And another important thing is that there are some period in the year, so you don't have the much hydro generation because of the dry condition. You don't have much hydro generation. So at that time, what will happen? So you have to operate the thermal power plant located in the western province, right? Then what will happen is that from this Colonna Vista station, the active power will be flow down. Will be flow to the down direction because there is a much requirement for the there are much grid substation there also. The southern part also there are a set of grid substation, and here Kiribati and somewhere here you have the Nuwara Badula. So those power station require those grid substation need the power. I know if you don't have the hydropower generation from this Lakshapana complex, what will happen is that power will flow from thermal plants to the via this Colonna grid substation. If you are generating more hydropower from the Lakshapana generation, what will happen is that active power will be flow in the upward direction. You know, so direction of the active power in this columnar transmission lines will be changed depend upon the generation. Right? Okay. So then this is the much important part in the any power system. So supply and demand balance. You know, supply and demand balance, and how they are going to balance the electricity demand from the consumers with the generation. You know, can someone tell me how they are going to do it? The first question is, how do we know how much people demand? Second one is, how do we equate the supply and demand? The last one is the important one. So what happens when the supply and demand is not matched? So we'll start from the last one. So what will happen in the power system if the demand and supply is not matched? Can someone tell me?
Frequency getting down.
Yeah, either frequency will be getting down, or it can be increase also, right? The two-way, it can be either decrease or increase. You know. Anyhow, the frequency will be changed. That's what you have to understand. You know, if there's an imbalance in the supply and demand, what will happen? Frequency will be changed. That is why we have to balance it. You know, in any AC power system, the main function is that in order to have the healthy power system, the supply and demand should be matched. Otherwise, you can't have this healthy power system, or power system will be collapsed finally. You know, it will be collapsed. So as we know that if there is unbalance, the frequency change. So you can use the frequency as the indicator. You know, that is how they know whether they have balanced the supply and demand. Right. So this figure explain what is happening. The consumers need the demand, the producers need the general supply. You know, if demand is higher than the generation, what happens? Frequency decreasing. If it is other way, if you are generating more power than the demand, what will happen? Frequency will be increased. You know, frequency will be increased. So that is why we need to balance it, right? So this will explain how it is happening actually. Right? You might already know synchronous generator. So basically synchronous generator, if you consider the rotor, there you have the two torques, right? one is the mechanical torque, other one is the electrical torque. So mechanical torque is the which one you apply basically using a turbines, right? The electrical torque is the one which applied because of the current flow through the stator, right? So if the mechanical torque is higher than the electrical torque, what will happen? What will happen to the rotor of the generator? Now mechanical torque is higher than the electrical torque. What will happen?
Rotor will accelerate.
Rotor will accelerate, then the speed of the rotor will increase, right? Accelerating means the speed is going to increase, right? The speed is going to increase. Then if the, in the synchronous generator, the basic principle is that the whatever the frequency or whatever the voltage it generates, right? There you will have a particular frequency. That frequency is proportional to the speed of the rotor. So that is the main feature of the synchronous generator, right? So you might already know this equation, right? Ns equal 124 T, So if it is going to change the speed of the rotor, what will happen? The frequency will be changed. That is how the frequency is going to change. The first thing happen is that demand and supply is not balanced, means the mechanical torque, in this case mechanical torque is greater than electrical torque, then the speed of the rotor increase, then what happen is that frequency will be increased. In other way, what is happening, if the mechanical torque is less than the electrical torque, the rotor will be decelerate, that means frequency will be drop. That is what happened. That is why we have to balance it. You have to balance it always, the supply and demand. And this shows you the SCADA screen of the control center, where they have monitoring the generation, right? Monitoring the generation. If you start from the left side, you can see the hydro generation, then in the middle thermal generation, and on the right side you can see the NCRE generation. NCRE generation, so at top you can see this total generation. Actually the load curve that you have seen just before, the few slides before, is plot using this total generation. It is not actually the demand. There is no way to measure the demand. So what they are doing is that they just measure the generation, because that there's a few number of power plants. So easily you can through the SCADA you can collect those values and add up and get the total value. So then they are plotting this total generation. Actually, we are consider it as a demand curve, and demand curve, right? And here again, you can see I told you that they are going to actually balance two things, right? Not only the active power and the reactive power. So this first row show you the active power generation of the power plant. Then the second row show you the reactive power, reactive power, right? So this is the control room or the system control center, the control room. So here the important thing that you have to notice is that, so this is the transmission network. Can you see the frequency meters there displays? 1, 2, 3, 4, 5, 6 frequency meters are there. So why they have this frequency displays? So this is the what they use to know whether they have balanced it. They're not going to measure the demand and check whether they have balanced it, right? They just observe the frequency, only the frequency. By observing the frequency, they know what has happened. If frequency is somewhere about 50 hertz, that means they have balanced it. If frequency is dropping, they know that what now the demand is higher than the generation. If frequencies keep on increasing, they know that now the generation is higher than the demand. So that is how they identify, right? So this again explain the what is happening in the synchronous generator. I'll skip it. So how the frequency is dropping. And this one is important, the inertia response. What is meant by the inertia response, right? So if you consider synchronous generator, it's a that rotor is rotating, it's a big mass, big mass. So it has particular inertia, particular inertia. In other way, because of that inertia, what happens is it has a particular stored kinetic energy, right? So this diagram explain what is meant by the inertia. So just forget about generator. So it is if you consider the as it is, it's just the water flow, right? So there's a water inlet and there's a water outlet. So if this inlet and outlet, inflow and outflow is equal, what happens? The level of this water will not change. Level of this water will not change. Now let's say I stop this input, right? I stop the input. So is that affect the demand? Just think using the water, right? Now I just, let's say I have the capability of stopping the water from the top, Is that affect the
No.
water flow outflow? No.
No.
So you have to understand that whether you are generating or not, our demand is not going to affect, not going to change. What, in other way, in terms of electricity, the consumers will consume whatever the value they need. They don't know whether we are generating or not, right? That you have to keep in mind. So unless you have changed this tap position here, this water flow will not affect. Clear? So by stopping the input water, that won't affect this demand or that output water flow. What will happen is that is still the same rate, at same rate water will be flow out. Now you don't have the input, the water coming into the vessel. What will happen to this level? What will happen to this level?
Level will reduce.
Level will reduce. Level will reduce. Level will reduce. Now you don't have the input, but output is still there, say in the same rate, So how they are providing the output in the same rate? Because of the water inside this vessel. Can you understand? Even without having the generation, you can supply the demand because of the water stored there. So that is when it comes to the synchronous generator, that is we call as the inertia. The synchronous generator can supply the electricity demand, electricity power out by reducing its kinetic energy, its own kinetic energy, because it's a rotating mass. It has a particular stored kinetic energy. Whenever you don't have the mechanical input, enough mechanical input, what happens is that the generator itself reduce its speed and release its kinetic energy as the electrical energy. That is why the frequency is dropping. Frequency is dropping, right? So that phenomena is explained here, right? What you have to understand is that the inertia, whenever there is no matching of generation and demand, if we are not going to match the generation and demand, first thing happen is that because of the inertia of the synchronous generators, and because of the inertia, generators try to supply the demand themselves by reducing their speed, by reducing their speed. So that is the first response come from the generators. So whenever the supply and demand is not balanced, or if you are not going to generate equal to the demand, the demand is not going to change because they will consume as they wish. Then what will happen? Generators itself reduce their kinetic energy and release that as the electric energy into the system. So that is called as the inertia response. The inertia response is the what which comes first. So again, the value of the inertia response will be changed depending upon the number of machines you have in the system. If you have only, let's assume if you have only 10 machines, and another case we have the 20 machines. So in the case you have the 20 machine, you will have the more inertia response as you have the more power plant. So all of them will be add them together, and it is more. Got it? And if you consider the time of the day again, what will happen is that the inertia of the system will be changed. So inertia is actually calculated for the one machine. Then for the whole system, you can calculate the system inertia, right? Then this is the frequency control thing in Sri Lanka. You know that in order to do that thing, supply and demand balancing, now what we are going to monitor is the frequency. What we are monitoring is the frequency. So by controlling the frequency, we are going to control the supply and demand. So we are going to balance the supply and demand. It's called as the frequency control. So first response, as I told you, it's the inertia response. If there's an imbalance, the first one comes is the inertia response. Then after that, there's something called frequency control machine in the at particular time. So there's a one power plant which monitor the frequency and change its generation automatically. That is called the frequency controlling plant. Other than that plant, that frequency controlling plant, all other power generators, we are calling they are pre-governor mode. That means that you might already know that what is meant by the governor, right? So there's a governor in all generators. You have the governor, which is the one which controls the speed of the generator, right? The speed of the generators. So that is the equipment in the power plant which control the mechanical power actually. Whenever the governor observe the speed change, it will change the mechanical power and try to bring back the speed into the rated speed. So other than the frequency control machine, all the generators are operating at the pre-governor. That is, pre-governor means governor is capable to respond to the speed difference or frequency differences. So all other generators will respond, but so frequency controlling plant will respond more. Because its droop is less than the other generators. I think you have the idea about the droop, right? I'm not going to explain. So frequency controlling machine will have the droop setting of 2%. The other plant will have the higher droops, right? So this explains what's happened. So let's say in this case, the according to this figure, you can figure out that Victoria Power Station has a smaller droop, and Kotmale Power Station you have the higher droop, right? It's 4%, and here it is less than 2%, right? So now you can understand what is happening. So this x-axis show you the power. Actually, this power is the mechanical power. So this droop setting is actually for the governor. That setting is for the governor. What this value say? What is its real meaning is that, for example, if the frequency is dropped from 50 hertz to 49.8, there's a 0.2 hertz difference, right? Drop. Now in the Victoria Power Station, it tells the governor has to increase the mechanical power by 7. Earlier it is at 50, now it is at 57. That is the difference is how much? 7 megawatt. So this will tell its governor to increase the 7 megawatt. In other case, in the Kotmale Power Station, what happened? It also see the same frequency drop. But now as its droop is 4%, what's happened is that there's only 2 megawatt of difference. In other way, in the Kotmale Power Station, what happened is that its governor tells its governor try to increase only 2 megawatt. Victoria Power Station try to increase 7 megawatt. So therefore, we are calling the Victoria Power Station as the frequency controlling plant. What is happening is that the Victoria Power Station will increase the 7 megawatt and it will correct the frequency. So Kotmale Power Station do not have, it's not required to increase because the Victoria one is responding first. So these are the power plants that is capable of doing that frequency control, right? And there's another thing which is important. We are calling it as the spinning reserve. What do you mean by understand by the spinning? Spinning? Can one of you tell me what is mean by the spinning? Just the literal meaning of the spinning? Hello? Are you following me? What is mean by spinning? So can some of you tell me what is mean by spinning?
Rotating.
Rotating, right? Spinning means rotating, right? So spinning reserve means now once the machine is synchronized into the system, or once the generator is connected into the system, So it is spinning, it is rotating, So in this case, we have to consider the machines, generators, which are connected into the system, connected into the system. That is the meaning of the spinning, So once you connect the machine into the system, sometimes you might operate it at full load, so whatever the full capacity, or sometimes you might operate it in a half load or somewhere less than the full capacity. For example, if you consider Victoria Power Station, its full capacity is 70 megawatt. Now let's say you are operating at 50 megawatt at this moment. At this moment it is only at the 50 megawatt. There's a difference from the full capacity. Another 20 megawatt you can increase if you want. That another 20 megawatt, we are called as the reserve. If you consider just the Victoria Power Station, the 20 megawatt is the reserve. Emergency increase. That is called like that. If you consider there are power plants, you can add that. So that total value is called as the total reserve. And if you divide the number by the total general, it is percentage. So
As we conclude today's webinar, I would like to invite Kavinda Tisudania.
Pansini say will come again. So wait. Guys, please remain on the meeting. So we can hear you. Pansini, please give host to the So I think you can share the screen now, sir.
okay. takes time. No, I think you can. No, I think you can.
Yes. Yes.
So that is mean by the. Can you hear me now?
Yes, sir.
Okay. So that is mean by the spinning wheel, right? So usually it is supposed to.
I think you are not in the correct slides.
Spinning wheel. Wait. So is the slides are. Can you see the slides are moving now?
Yeah, still slides are not moving, sir, but we can see the slides partially.
I think if I put it into the slideshow, it is not showing, right? So we just do it using this screen. Okay,
Sir, I think it's okay, sir.
it's
We
okay
can-
because
Yeah,
it can, right?
we
So
can
when I
proceed.
discuss in the spinning ratio, right? Spinning ratio margin, so that value should be 5%, right? 5%, right? So next thing is that this shows the timeline activity, I know. So as I told you, the first thing, whenever there is an imbalance between the supply and demand, so first thing comes is the inertia response, then the governor, then as a third, frequency control, then finally human intervention. The economic dispatch means the human intervention, right? So someone has to involve there and do the change the generation here and there, right? So this is just show you the frequency rate, how the frequency is going to change, you know. And this equation, I think you do you have any idea about the swing equation? So you can derive the swing equation for the data, then again combine those equations to the whole system and define a swing equation for the whole system. So swing equation is the one which governs the relation between the power error and the frequency error, you know. So according to the swing equation, you will have the frequency changing, right? So in this case, now let's say 50 years. So due to some disturbance, what has happened is that frequency has been dropped. I know frequency has been dropped. If you don't have the governor control or the governor response, what will happen? The frequency will be sometimes it can be settled in some another frequency. So if you want to bring it back into the 50, you need the governor control, right? With the governor control, it will try to increase it, but still you will have the frequency error, right? Now, so frequency is the which takes the system frequency back to 50 hertz, right? So that is what you have to understand. So I'll omit this slide. So here you can see that. So when you have the frequency controlling, it will take the frequency back to 50 hertz. So right. Then we'll skip this slide because take time. So I'll move this. You have the thermal dispatch, merit road, right? So if you consider the hydropower plants usually operated within this priority. You can see that first of all, the water is allocated for the drinking purposes, then the drainage and the environment, then the irrigation, and finally only power. You know, so you have to understand that the last of all of these requirements, once the satisfied, if there is enough water, then only we can use the water into the power generation. You know, so usually what happens in the country is that so there's a meeting weekly with this four organization. One is the Mahali Authority, then the Water Board, Irrigation Department, and Electricity Board. The representative from all these four organizations meet in a meeting and discuss and come to a conclusion how they are going to operate the hydropower station within that week. Then finally, they'll output something called the water management directives. I know. So these directives are the one used by the control center in order to operate the hydropower plants. You know. So basically, the hydro generation depend upon this requirement of the water board and the irrigation department. Right. Then we'll move to the thermal dispatch, and this is again another important thing. So you have converted the reservoir water capacity into gigawatt hours, right? Energy, So this show you the total storage variation. That means if you at the all the energy stored in the reservoirs, all reservoirs, it will be somewhere around 1,200, So now this graph shows you how the variation of the storage. So January, February, March, if you observe, always what has happened is that the total storage has decreased. Because you know that these first 3 months is most of the time dry period, you are not getting rainfalls. Therefore, the water level is keep on decreasing. That means our storage is decreasing. And then you can see the hikes at in May and another on September, October. You know that this is actually because of the monsoon rainfall. So in May and from starting from May, you are getting the what is called the southwest monsoon, and from October onward, you are getting what is called the northeast monsoon. So those monsoon rainfalls are the most, the biggest inflow you are getting into the reservoirs. But you can see that some years you don't have the monsoon, so then you don't have that high. For example, if you consider this gray color one, there you don't see any hike here, and that means you here what has happened is that southwest monsoon has failed, and then we moved to the merit order dispatch. So in the merit order dispatch, actually it considers the dispatching of the thermal power plants, right? Thermal power plants. So before we move into the thermal dispatch, we should have some idea about the cost, right? Cost of the thermal plant. So there are actually several costs you can define, right? One thing is that unit cost, that means to generate unit of one energy, that's 1 megawatt, 1 kilowatt hours. What is the cost? That is mean by the simply unit cost. Then there's another cost we define as a no load cost, right? No load cost for some power plants, whether you taken the electric out or not. So its cost is the cost for maintaining the thermodynamic cycle. Thermodynamic cycle, you have to burn. So even you have the output electric power, still what you have to do is that you have to burn the fuel. So that is called as the no load cost, right? Then there is another cost which is defined as the incremental cost. That is once you have started the plant and synchronized into the system. So what will power in order to increase the or decrease additional unit, additional units. That means the incremental cost, it forget about the no load cost, right? Then again, there's another cost which is defined as start stop cost. That is there are some power plants, thermal plants, which use the different fuel in order to start and stop. So start and stop, they define another cost separately, right? And capacity cost is the one which is actually not used for dispatching. So whether we have operated that plant or not, we have to pay this capacity cost. Capacity cost basically it consists the loan installment. You know that when in order to build the power plant, you need huge money. Usually they are supplied the capital from using a bank loan. So then they have to pay that loan back. So there's a monthly installment. So when the thermal power plant agreed with the CEB, they put this capacity cost in order to cover that loan component. So the independent from the operation of the power plant, this capacity cost we have to pay always. Therefore this capacity cost is not used to for the dispatch purposes, right? So then this will sure. I think yeah. So here is just show you the how you are getting the cost, right? So this y-axis show you the cost per hour, and the x-axis show you the output megawatt. So if you draw the one line, let's say for example you are operating at 30 megawatt. So gradient of this line will give you the unit cost, you know, because y difference give you the cost per hour, and the x difference give you the output power. So if you divide those two, you'll get the unit cost, you know. Then incremental cost means the gradient of that curve, you know, that will give you the additional cost that you have to spend in order to increase or decrease the 1 unit. So what has happened is that it forget this total no load cost. You know, in this slide it shows you that no load cost, right? No load cost means, so even your output power is 0, there's some cost. You know, this axis shows you the cost per hour, right? So now can you see that still there you are getting a value, you know? So that means even you don't have the output power, you have to burn the fuel in order to keep the thermodynamic cycle. So this show you the sum of the no load cost of power plant, right? The combined cycle, then West Coast Power and Sopadani, like that, right? So then we'll move to quickly. There actually basically two parts in the thermal dispatch. One is the unit commitment, and another one is the economic dispatch. Unit commitment means what you are considering when machines are starting and stopping, right? The economic dispatch is that once you have started the machine, then during the operation of that machine, how you are going to minimize the cost, right? So in this question, so it shows you that the two cases, right? Two cases. The one case is that you have the generator A, and other one is you have the generator B. Then the unit cost of the generator A is 16 kilowatt per kilowatt hours. For the generator B, unit cost is 20 per kilowatt hours. Both generators have the startup cost. The generator A startup cost is 10 million and generator B startup cost is 6 million, right? So then if you calculate the total cost means the energy cost plus the startup cost, right? Energy cost plus the startup cost, right? So energy cost you can calculate simply by multiplying this unit cost with the megawatt 50 and again multiply by number of hours, right? Now we are going to operate this power generator A or generator B for 15 hours. You know, simply multiplying 50 into 16 into 15 hours will give you the energy cost. You know, that is somewhere around 0.8 million. Then you have to add it with the startup cost, right? Then in this case, again, you have to do the same thing. So finally, anyhow, you are getting the total cost for generator A, you are getting 22 million, and generator B, you are getting 21 million, right? Now, can you see the difference? If you just consider only the unit cost, you know, by forgetting the startup cost, you can see that generator A is the most, what you can say, generator A is the what we have to operate, because there you have a least unit cost, you know. But when the startup cost comes into action, what happens is that now generator B is the what we have to select, right? So it total cost is 21 million, right? So that's what you have to understand. The merit order does not mean that just operating the power plant from the least cost plant to the highest one. So we have to consider so many things. For example, if you do this recalculation without time 15 hours, so there will be a one value, one figure, this will change the from generator B to generator A. You know, there will be a break-even point depend upon this time period. So in the unit commitment, you have to consider the startup cost plus the time duration and the unit cost. You know, by considering all these three parameters only, you can decide which option is the most least cost one. Right? So this is again another example, right? So we'll just omit it and we'll move to the economic dispatch, right? The economic means, so once you have synchronized the machine into the system, so then in the steady state operation, so you just forget about the start and stop, you know. Then during that, once you're synchronized into the system, again, sometimes you might have to decrease or increase the generation because you know that demand is keep on changing. So without stopping it, you have to decrease or increase the generation. You know, so there what we are doing is that we just do not consider about the startup cost, right? Because we have already synchronized the plant or we have already started the plant. So you don't need to consider about the start stop cost, right? So what we have to do is that we have to compare the generation using the incremental cost or the unit cost, right? So in this example, you have the two plants, plant A and plant B. The one plant capacity is the plant A capacity is 100 megawatt. Its unit cost is 9 per kilowatt hour. In plant B, it's a combined cycle plant. Its capacity is 150. And in the case of combined cycle plant, I don't know whether you know that its unit cost is changed depend upon the megawatt. You know. Now in this case, at 150, its unit cost is 12. If it is operating at 100 megawatt, unit cost is 40. You know, now the requirement is you have to increase another 200 megawatt, right? You have to increase another 200 megawatt. So we'll consider two options, right? Because in order to get the 200 megawatt, one option is that you can get the 150 megawatt from the plant B and another 50 from plant A, right? That is one option. The other option is you can get the 100 megawatt from plant A and another 100 from the plant B, right? Another 100 from the plant B. So you can do the calculation and see which option is best, right? So these are the two options, right, that I have told you. The option one is you are loading the plant A 100 megawatt, then take the balance from the plant B. The option two is that combined cycle plant is operated at its full load, and remaining 50 megawatt is taken from the plant A, right? So if you do the calculation, so this will be the answers, you know. So you can see that option 2 is the most economical one. So where you are getting the less value, right? If you compare the cost, option 2 is the best one. Again, if you change the number of hours and things, not number of hours, if you change this, depend upon this unit cost, this answer would be changed, right? As I have selected these values here, we are getting this here. So now in this case, option 2 is best. Option 2 means what? Option 2 means you have to get the full load from the combined cycle plant and the remaining 50 from the other plant. That means if you compare, now it says that you have to operate this combined cycle plant at full load, right? But if you compare the unit cost, it is too, you know, if you just compare the unit cost, you might feel that you have to operate the plant A fully and then you get the remaining 100 from plant B, because plant A unit cost is 9, right? But actually what you are getting, the correct one is you have to operate the combined cycle plant at the full load, even though it is unit cost is, then only you can take the remaining 50 from the other plant. So what you have to understand is that the merit order dispatch does not mean just the dispatching the plant according to its unit cost. It is much complex thing, right? It is much complex thing, and it depends upon the number of hours and that megawatt amount that you need, right? Hello.
Sir, we can hear you.
Yeah. So this presentation also is difficult to start the slide slow. So I will do in this mode, right? So this is just about the total failure occurred on last total failure on 2023, 9th December, right? 9th December, somewhere around this time. So what has happened is that, so this is just show you the what has happened there. So this is what has happened, right? So I think you have no idea about the Mahali generation, Mahali complex, and how it is connected within the system, right? So there you have the two lines to Biagama and two lines to New Habarana. And from that side you have the connection via the Pantame power station, right? Pantame is 220 transformers. It is connected to the rest of the system, you know. So in this case, what has happened is that, so at that moment, all the Mahali generation was about 665 megawatt. You know, if you add all Kotmale, Victoria, and the upper Kotmale generation, it is this much, right? So then what has happened is that this Kotmale Biagama both line has been tripped. You know, Kotmale Biagama both line has been tripped. So once this line is tripped, so that generation try to flow where. So already the whatever the generation in these lines are the requirement of this load centers of the Colombo. You know, there's a power flow from Kotmale to Biagam. So if these two lines are not available, then that power will try to flow to the same place via another path. You know, so the next path is that this one. Kotmale to New Hampshire, New Hampshire to New Anwadapur, New Anwadapur, Lakpijay, like that, it should come there. You know, so next moment what is happening is that whatever the power has been flow from Kotmale to Biagama, adapt to this New Hampshire lines. You know, adapt to this New Hampshire line. Then what will happen? This Kotmale New Hampshire lines are overloaded. You know, overloaded. Because already there's some active power flowing in this line. On top of that, this Kotmale Biagama load is also going to add. You know, then what is happening? This Kotmale New Hampshire line, both lines are were tripped due to overload. You know, Kotmale Biagama line is because of some fault, right? Some fault in the network. But the Kotmale New Hampshire lines are tripping because of the overcap. You know, then what happens is that there is no path. No path for this Mahali generation to flow into the rest of the system. You know, Now you might have the question because there's another part to the runtime coupling transformers. But actually, at one point, somewhere in Badul or somewhere, it is disconnected. It is disconnected. So therefore, what is happening now? All of this 655 megawatt is rejecting from the system. Rejecting from the system. So what is happening is that the rest of the system cannot survive. Because there is a huge generation rejection. Then what will happen definitely? Frequency will be dropped down and system will collapse. Right? So that's what has happened in this case. So this shows you the frequency variation, right? This I think green color one. Green color line is the frequency. Right? Green color line is the frequency. So this is the initial point where Begum Kotmane both has been tripped at this moment, right? Then what has happened is that within I think 1 minute period, there's I think this is 72, yeah, 2 and somewhere 73, right? So just in 1 minute, what has happened is that Kotmale and New Harbour both line has been tripped. So thereafter, you can see that the frequencies rapidly drop down, and this is the point where total failure occurs. Right? So this graph, this show you the voltage and currents of the transition lines, right? So this is the starting point where Begum Kotmale both circuit has been tripped, right? And this green color one shows you the new Haberman circuit, right? New Haberman circuit. Then again, there's a two lines, right? Two circuits, right? Circuit 1 and 2, right? So first class, what has happened is circuit 1 trip, then that load is again added to the circuit 2. Circuit 2 also trip, within the same second, both line trip, right? That's what has happened, right? Then this show you the Mahali system failure, this green color line shows you the, I think should be green color one, the Begum voltage, Begum voltage. So you can see that how the voltage is dropping. So that is the point of failure. So then again here the green color one shows you the frequency, right? Not the frequency, sorry. Green color one shows you actually the it's again a voltage, right? It's again a 220 voltage at the Begum grid substation. So it's somewhere about 220 kilowatt, and after the blackout, what is happening is that it dropped to 0. The total failure means there's no voltage, right? So that is what has happened in 2023 total failure, Then, so when it comes to the restoration after total failure, so restoration take place as a separate system, it's a separate system. So this is just the restoration of Colombo. So Colombo sub-J and sub-H, there's a two big substation. So those two substations can be supplied using this current is a small GT. So I think sub-J and sub-J, one is the harbor, and other one is I can't remember what is that. Whatever the important substation, they are both. First thing is that those two substations can be supplied using the one of the GT, right? Then rest of the system is restoration is start separately as a Lakshapana and Samanalava and Mahal. So finally, all those subsystems connected or synchronize each other. So then only you can form the total transmission network, right? So when this is just show you the Lakshapana system. The one thing you have to understand is that so after total failure, you can't energize the whole system just using a one machine, right? So why is that? Now, once the failure occurred, if you just forget about that Kotmale Bigama line and Kotmale New Haganah line, rest of the lines are in the on position. I know the connections are there. So why you can't just connect another machine and energize the whole system? Can someone tell me what is the reason? Hello? Can someone tell me why you can't energize the whole system just using a one machine?
So we need to increase the system redundancy. The PUCSL guideline says that the unit capacity, one of
Hello?
the PUCSL guideline says that the highest unit capacity should be 20% lesser than the total generation of the system. Am I audible?
Hello? Yeah,
Am
I
I
got
audible?
your answer.
Yeah.
So that PUCSL requirement actually for the steady state or the smooth when the system is alive, you know. Okay. So now at this moment, the whole system is collapsed, but the transfer network is interconnected to each other. You know, I'm asking why one machine, whatever Victoria, Kotmale, whatever, one machine just connected into the system. And then what will happen? Our system will be energized suddenly. It is not possible, right? So what is the reason for that? So if it is possible, so after total failure, it won't take much time to restore it. Just you can connect one machine, whole system will be energized again. The one thing it is not possible is that at the moment total failure, let's say for example, demand was 2000 megawatt, you know. So if you just connect a one machine, that single machine cannot supply that much of demand, you know. That's the one reason, right? So that 2000 megawatt is supplied by so many generators. Now once the whole system collapses, by connecting only one machine, you can't supply that demand. Then definitely what will happen, whatever the first machine you are going to connect into the system will be tripped, right? Another reason is that, let's say now, in order to avoid that problem, you can disconnect the feeders. You know, you can disconnect all feeders. Then there won't be any demand. Only the transmission network going to be energized, right? Then at that moment, what happens? If you synchronize one machine to energize the whole system. The transmission lines, you might learn that. So if there is no current in the transmission line, or small current in the transmission line, its capacitance is higher. That means transmission lines are acting like a capacitors. You know that capacitors absorb the reactive power or inject the reactive power. Inject, right? Capacitors are injecting reactive power. So then what happen? All transmission lines, not only single, all system act like a capacitors. They generate the reactive power and pump into the network. So more reactive powers pump into the system. There's no consumers because we have already cut off the all 33 kV feeders. So no consumers, but transmission line pumping the reactive power into the system. Then what will happen? System voltage will be increased rapidly. Rapidly. Then again, whatever the machine you are going to energize will be tripped because of the overvoltage. That machine can't absorb that much of reactive power. Therefore, machine will be tripped. So in order to avoid those two issues, the way to restoration is that we have to start restoration part by part. Part by part. So what they are going to do is that using the first machine, it energizes only 2 or 3 transmission lines. Then that 2 or 3 transmission line will not generate that much of reactive power. Got it? Then the first machine can absorb that reactive power and survive. Right? That is why we are restoration is done as a subsystem. So one of the subsystem is Lakshapana. So you can, from this figure, you can understand this Navalakshabana line. It is going to energize from Navalakshabana to Kolpitiya to Athuviriya to Kolon Nav. First it will energize up to Kolon Nav. Then some of the feeders will be switched off. You know that there are 33 kV feeders in this substation. Those feeders will be switched off. And another thing you have to understand that it is just a single machine. It is not like the previous system where you have so many generators. So when you have only single machine, its inertia is very small. Frequency is going to fluctuate quickly. So therefore you have to switch on 33 kV feeders one by one. You can't just energize all the 33 kV feeders here. You have to switch on one feeder and wait until frequency settle down and then switch on the next one. Like that, you have to gradually load the generator. So it will take some time. It will take some time. So you can understand here, they have given some times. So it says that New Lakshman unit 1 was started at 1740. Then the next machine, Kolpiti unit 1 has been synchronized somewhere around 1855. Do you understand the time taken? Then
Yes, sir.
third machine, WBS unit 1, the Vibraswayant unit 1 has been synchronized at 1928. So this much of is time taken because machine has to be loaded in a. It's not like in the normal operation. Because of the less inertia, they have to do it in a very slow manner. That is why during a total failure, it takes some time. Which is not sometimes, it will take more time, right? Somewhere around 4 to 5 hours take to energize whole system. Right? So that is about the Lakshapana system. Then when it comes to the Mahali. So that's again. This is a Mahali system. And in this case, describe the upper Kotmale. Right? Restoration starts from the upper Kotmale. Now the upper Kotmale power plant will energize up to this. Initially, it will energize up to this Biagama Crest substation. Biagama Crest substation. Then you can switch on some feeders at the Biagama power station. Then you can extend one way to Sapugaskanda and another way to Kotugod, another way to Kalitis. So one by one, thereafter each of these transmission line are switching on and feeders are switched on. So same procedure take place. So you will have the Mahadi system and the Lakshapana system. So now in this case, these two systems are separate, not like the previous system. Before the total failure, you have a single system. Now you have the two systems. Two systems. Then again, you have another subsystem using the Samanala power station. That's again the same as the previous one. It will energize up to some risk substation. So you'll have another subsystem. And altogether you'll have three subsystems: Samanala system, Lakshapana system, and the Mahalia subsystem. Now, if you monitor the frequency, now before the total failure, when you have the healthy system, healthy transmission network, there's only one single system. If you measure the frequency at any point, it will have the same frequency. But in this case, what happened? Samanala frequency, if you compare with the Mahal frequency, at the same time, that will be two different values. That is why we are calling it a two system. So in order to make the full network again, you have to synchronize these subsystems. Synchronize. So in this case, what they have done is that the Mahali system and the Lakshapana system has been synchronized at the Pandipitiya Kolonava line using at the Pandipitiya substation. And the Samanala system and the Lakshapana system synchronized at the Lakshapana Balangoda lines using at the Balangoda this substation. I think I think you have the idea about that. Right? Can you remember the network? I don't have the network here. So Mahali and Lakshapana system connected at the Pandipitiya grid, and after that, the total system connected the Samanala power station at the Balangoda grid. So then you'll have the total network as before the total failure. So that is how they are after total failure restoration take place. Right? I think that's all I have to share with you. So shall we wind up? Do you have any questions? I think it does take some more than 2 hours. Okay. Sorry for the disturbance happened due to these network failures.
Thank you, Engineer Tanishka, for such an informative and thought-provoking session. Now we would like to open the floor for your questions. Please feel free to raise your hand or type your questions in the chat box. Let's make this an interactive session.
Can you explain about how StatCom help to the power system?
StatCom.
Yeah.
Okay, I think we have omit that side, the voltage control. So StatCom in the way that I think you're asking about the one which connected at Diagama, no?
Yes,
that?
sir. Yes.
Yeah. So it is capable of that like that. You know that the capacitor, you know that they are generate the reactive power and inject into the system. You know, so it will help to keep the system voltage. StatCom means it has the capability of both the capacitors and the inductors. You know, plus and minus. I think the Diagama one has the capacity of 100 megawatt. It has the capability of injecting the 100 megawatt, or it has the capability of absorbing the 100 megawatt, right? As I know the values. So that will help in case of if let's say now if the voltage is going to drop in the system, usually what is happening is that, so if you consider Western Province, that is the load center. So at the times where we are operating the hydro generation, so reactive power should be flow from those generators to the Colombo or the Western Province. You know, usually what is happening is that the voltage would be less than voltage will be dropped because there is no much reactive power, and again the demand is high. You know, when the demand is higher, the voltage drop is higher because of the current drop. Because of the current, voltage drop is higher, right? So then if you can have some system there which supply the reactive power as a capacitor, that will help to build up the system voltage. The other way is that during some now usually the system voltage in the Biagama, Kotugoda, like the Western Points substation, is not going to increase unless there's a disturbance. You know, in case of a disturbance, if there's a voltage high, so that StatCom can absorb the reactive power and stabilize the system voltage. So like the StatCom, they have installed reactors at New Anuradhapura and Mana grid substation. So those are just reactors, variable shunt reactors. They just only absorb the reactive power, because you know that in the northern part, the demand is much less. Therefore, usually during the night time, voltages go beyond the limits. So at that time, what they are doing is that they switch on the reactors. So those reactors will absorb the reactive power and reduce the system voltage. Right? Got it?
Yes, sir. Thank you, sir. Sir, I have another question. I saw in the grid substation the reactors are capacitor banks were connected in star and delta. Uh, uh, they told us like that scenario, but we don't understand what they told to us.
Stand delta.
Yeah.
Capacitor banks.
Yes, sir.
Actually, I also do not have any idea about that. But I'll share the number with you. So I'll find out and let you know, because I don't have much idea, but because I have worked in the system control center for 11 years, so I don't have any experience in the maintenance, the transmission maintenance. So in order to answer your question, I don't have the much knowledge regarding why it is the stand delta connection. right?
Okay, sir.
So sorry for that. I'll share my number.
Okay, sir.
Can you see my number? This is the WhatsApp number. Just drop me a message. I'll check it with the relevant guys or who has the knowledge about that, and I'll let you know.
It's time to express our gratitude for Sir Danushka's significant contribution. We would like to present you with a token of appreciation as a symbol of our gratitude. We're so grateful for your support, sir. It means a lot to us. Thank you.
Thank you very much. If you have any question, I have shared the number with you. You can drop me message via the WhatsApp, right? Thanks again for inviting me for this session. I think you might have got something, right? And wish you all the best.
As we conclude today's webinar, I would like to invite Kavinda Tesadenia, Secretary of IEEE Power and Energy Society, SEUSL, to extend our heartfelt gratitude to everyone who made this event a success. Kavinda, over to you.
Thank you, Siluni. Good evening, everyone. As we come to the conclusion of this enlightening webinar, it's my honor and privilege to extend our heartfelt gratitude to all who contributed to its success. First and foremost, a big thank you to our esteemed guest speaker, Engineer Danushka Bandara. Your expertise and insights into the operations of our national grid have been incredibly valuable. The knowledge you shared has truly deepened our understanding of this critical field. I would also like to thank the organizers from both of the IEEE student branch of Kataravala Defense University and Southeastern University's Power and Energy Society. Your teamwork and dedication made this event possible. To our participants, your engagement and curiosity throughout this session were truly inspiring. It's your enthusiasm for learning that motivates us to organize events like this. Finally, to all attendees, thank you for taking the time to join us this evening. We hope this session was insightful and provided you with a deeper appreciation for the intricacies of national control system. Let's continue to stay connected, learn together, and grow as a community passionate about energy and innovation. Thank you once again, and have a great evening.
Thank you, Kavinda, for your kind words of appreciation. And to all our attendees, thank you for being a part of this insightful session. We hope you find it valuable and inspiring. Stay tuned for more events organized by the PES Club of Kuthalawala Defense University and the IEEE Power and Energy Society.